Hello, my name is Wyatt Rabita, and this is my Physics 2212 Lab 6 presentation. Introduction. The purpose of this lab is to measure and visualize the effect of the eddy currents on a falling magnet through a thick tube of aluminum foil. The model is used to compare ideal results to the actual experimental results. The materials used in this lab are aluminum foil, a bar magnet, a smartphone, a meter stick, and WebVPython. And here are the brief results of the experiment. The average time in the tube that we observed was 0.288 seconds, and the time in the tube of the model was 1.666 seconds. Initial conditions of the lab. The system is the magnet and the surroundings are everything else. The length of the tube was 0.44 meters. The width of the tube was 0.013 meters. The inner width of the tube was 0.0135 meters. The magnet mass was 0.0334 kilograms, and the magnet mu value was 1.11. Timetables. Using the smartphone, we recorded the magnet dropping through the tube at 60 fps. This was repeated 5 times, and the time the magnet was in the foil was averaged to give a result. As you can see, the result is 0.288 seconds. Modeling the experiment. Using WebVPython, I modeled the experiment using the starter code. On the top right, we have the initial conditions listed out for the code. The middle defines a function that returns the magnetic dipole given a mu value and an observation point. And the bottom function returns the change in flux given the magnet object and a segment of the tube object labeled ring. Modeling the experiment, Part 2. This whole section of code finds the force of gravity on the magnet and uses the functions from the previous slide to calculate the magnetic force the magnet experiences as it falls through the tube. Visualization and data. As seen in the graph, the velocity remains constant for a large portion of time. This happens when the net force equals 0, meaning F magnetic and F grav are equal in magnitude and direction. Interpreting the data. Question. Which color corresponds to clockwise current and which counterclockwise? Answer. When viewed from above, the red color represents the counterclockwise current, while the blue represents the clockwise current. We arrive at this answer by using Lenz's law and the right-hand rule. Question. What happens to the dynamics of the system when you flip the magnet around? Answer. If you flip the magnet, it would fall the same way, but the current directions would be inverse. Question. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? Answer. The time of the real-world system, 0.288 seconds, was much shorter than the computational model, 1.666 seconds. My suspicion for this difference lies in the magnetic moment value, as well as other errors that were made. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The plot shows that the magnetic force cancels out the gravitational force for the time that the magnet is falling inside the tube. Potential sources for error. 1. The original value for mu found in Lab 4 was 111, which caused the simulation to explode. So, for the purpose of this lab, I divided it by 100. 2. The model made did not account for any other forces, such as air drag or normal forces, if the magnet ever hit the walls of the tube. And 3. The magnet was not dropped from the same location for every trial, and the position of the tube also varied. Extra questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity of the conductor, R, was decreased, then by Ohm's law, V equals IR, the current induced would be stronger, providing a much stronger magnetic force, slowing the magnet even further as it descends through the tube. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? If slots were cut into the tube, the current would be interrupted at the locations of those slots, meaning that the eddy currents cannot provide as strong a force to oppose the gravity affecting the magnet as it falls. And that's it for my lab. Thank you for your time.